This video is on section 11.6, Principles of Counting. In this section, we will talk about the fundamental principle of counting, and we will also count permutations and combinations. Here is our first example, and it's about Betty's Bodacious Burger Truck. And there are 3 different kinds of patties, illustrated here. 3 different types of cheese, illustrated here, and 2 different types of buns. All of these are the choices that you have. And we want to know how many different combinations of burgers can be made. On the next slide, I'm going to show you one way of solving this. One way of solving this is by using something called a tree diagram. And it would start like this. We'll start with the 3 types of patties. There's a sirloin patty, a turkey patty, and then of course there is a veggie patty. Now once you choose the type of patty, let's say you choose the sirloin patty. Well, you now have 3 choices of cheese: cheddar, Swiss, or Munster. Once you choose your cheese, then you have 2 choices for the buns. So 2 choices here, sesame or wheat, or if you choose this one, 2 choices, sesame or wheat, same thing here. So really, if you choose a sirloin burger, if you look at this, this tells you the total number of possibilities just for a sirloin burger. That would be 6. Well, the same thing can happen with a turkey burger. Maybe you choose turkey instead. Well, if you choose turkey, you still have 3 cheese choices. But then you have 2 bun choices as well. So this one has 6 choices. And then, you probably guessed it, this one also has 6 choices. So if I add these all together, there are a possibility of making 18 different burgers. See if you can give this a try. Let's talk about pizza now. Maybe you're getting hungry. So we have 2 crust choices, thick or thin. Once you choose your crust type, there is a choice of 6 toppings. So from here, 6 choices, and from here, 6 choices. 1, 2, 3. So if you add them all up, there are 12 different pizza types that you could choose. This is called the fundamental principle of counting. And basically, the fundamental principle of counting says that there are m different ways, then there are n different ways. If you want to find how many total ways there are, you simply multiply those. So if we go back to that burger example, we had 3 choices for the patty, 3 choices for the cheese, and 2 choices for the bun. Well, this is 9 times 2 is 18. So it's a little bit easier than actually sketching out the number tree each time. Let's look at another example. Suppose you have a math quiz with 8 multiple choice questions, and each of those have 4 choices. There are also 2 true-false questions. We want to find how many different ways you can answer the questions on this test. Now, of course, you can make a number tree, but once you see this answer, you will see why that's probably not a very efficient method. Instead, we can do the following. We have 8 multiple choice questions, and they each have 4 choices. So there are 8 questions, 8 of these, and they each have 4 choices. 4 choices for this question, so on and so forth. And then finally, there are 2 true-false questions. Well, there are 2 answers, either true or false. So these are each 2. Well, if you plug this into your calculator, remember this is 4 to the power of 8 times 2 squared. This will give you 262,144 ways to answer this test. Doesn't that make you want to become a teacher? Thank goodness for Scantrons. Let's look at another example. Suppose we have a license plate and it is composed of 3 letters followed by 3 digits. And we have 3 different scenarios that we are going to take a look at. So let's let this represent the letters, and then this is going to be the digits. Let's see what our requirements are here. It says that we can have repetition of the letters is not allowed. Okay, so this is the only requirement. That means whatever letter this is, it cannot be repeated here or here. So let's think of how many choices we have for letters. We should know that there are 26 letters in the alphabet. And if you don't believe me, go ahead and count. But that means I have 26 choices for the first letter. But if I cannot repeat that in the second letter, one of those has already been used, which means there are 25 others remaining, and that's the number of choices I have. Furthermore, when I go to find my third digit, now I can't use 2 numbers. So, I'm sorry, 2 letters. So now I'm down to 24 choices here. Now there are no restrictions on the digits, and one thing to be cautious of is our digits, since it's not mentioned, we will use digits 0 through 9, which means there are 10 choices. So 10 choices here, here, and here, because we can repeat digits if necessary. So I just throw this into my calculator and I end up with 15,600,000. A lot of choices. Let's look at the next example. So I'm going to set this up the same way. I have 3 letters and 3 digits. And it says repetition of letters is allowed. So now I have 26 choices here. I can repeat that if I want, so I have 26 choices here and here. The digits stay the same. When I multiply all of this out, I get 17,576,000. All right, let's look at this last example. It says repetition of the letters are allowed, so that would be 26, 26, and 26, but the number may not begin with 0. Okay, so now we have a restriction on this piece only. That cannot be 0. Well, if there are 10 digits and one of them is 0, that means I only have 9 choices here. But there are no other restrictions, so the other 2 digits can be 10 choices. When I multiply this out, I get 15,818,400. See if you can give this one a try. Okay, well, now this alarm is made up of 2 letters followed by 4 digits. And there are no restrictions on letters or digits in part A. So 26 choices for each of these and 10 choices for each of these, giving me 6,760,000 choices. All right, now in part B, this is where it gets a little more interesting. I think it's helpful to draw these blanks. Now it says no letter or digit may be used more than once. Okay, so when I'm looking at the letters, I have 26 choices for this one, but I'm going to use one of those, so I then have 25 choices here because we cannot repeat our digits. Similarly, I have 10 choices for my first digit, 9 for the second, 8, and 7. Multiplying this out, I get 3,276,000. Now I'm showing you so many examples because sometimes this is a little challenging to wrap your head around, and I want to make sure that you have a good understanding. So please pause this and see if you can answer this one correctly. A quiz has 4 true-false questions and 6 multiple choice questions. And the multiple choice questions have 5 possible answers. So I want to find how many ways the questions can be answered. So for the true-false questions, I have 4 of them, and they have 2 possible answers. Now the multiple choice questions, there are 6 of them, and they each have 5 possible answers. So 5 times 5 times 5, 6 times. Multiplying this out, you should get 250,000. So that's a lot of different ways you can answer a test. We are working towards finding permutations. And a permutation is an ordered arrangement of objects. So it's important to know that the order matters. Okay, so let's look at some examples here. It says, in how many ways may the letters in the word ice be arranged? Okay, well, let's write out these possibilities. Ice is not a long word. We can proceed and write some possibilities. So ICE would be 1. Well, let's keep the first digit and switch the second 2. Maybe we will start with E instead. If I start with E, I could have IC, or I could flip-flop those and have CI. Or I could start with C and have IE, or flip those and have EI. There are not any other combinations here. So if I count these up, there are 6 possible ways to arrange the letters in the word ice. This is basically a permutation. In our previous example, the letters were distinguishable because they were different. They are distinct. I is different than C is different than E. So they are distinguishable. They are distinct. They are different. So what I can do is, instead of writing all of the possibilities, I can use a factorial. In our previous example, ice, there are three elements, I, C, and E. So 3 factorial is 3 times 2 times 1, which is 6. We found that the previous example did have a result of 6, and this is a simpler way of finding it. The thing you have to be careful of, though, is that the elements are distinguishable. They are different. Now, sometimes the elements are indistinguishable. For example, if I have the word 9, if I switch these two ends, I still end up with the same result. So it's indistinguishable. That means they're duplicates, basically. And if there are duplicates, what we need to do is we need to eliminate those, or we need to remove those somehow. And the way we remove those duplicates is in this manner. So whatever our duplicates are, they will go down here. And that basically tells us how to remove that repetition or those duplicates. Let's look at an example. Okay, so let's say we have 5 people and we want to put them in line. Okay, so again, sometimes it's helpful to draw this out. Well, for the first spot in line, there are 5 choices. But then in the second spot, we've already used one of those 5, so I have 4 choices for the second spot in line. 3 and 2 and 1. So notice that this is 5 factorial, because Bobby is different than Susie, is different than Jane, is different than so on and so forth. This results in 120. So no 2 people are the same, so these are 5 distinguishable people. But now in example 6, it says determine the number of ways 5 chess pawns may be lined up if 3 are black and 2 are white. Well, now we have some duplicates, don't we? So what we need to do is we'll use that little formula. We have all the possible choices, so of these 5 chess pawns, but the duplicates go down here. 3 of them are black, 2 of them are white. And then we just solve this. Remember, we can write this as 5 times 4 times 3 factorial. The 3 factorials cancel. 20 divided by 2 is 10. So 10 possibilities here. See if you can give this one a try. Now here, we want to arrange 7 different books on a bookshelf. Now, they have specifically told us we have different books, so there are no repeats here. Because there are no repeats, they're all distinguishable, which means our answer will be 7 factorial. And this is 5040. Now part B is a little bit different. We want to figure out the number of ways we can arrange the letters in the word riffraff. Okay, well, it's helpful to figure out how many letters there are. There are 8 total letters or spots. Okay, 8. Now, if we reorder these, I'm going to have duplicates. So there are some non-distinguishable items. In fact, there are 2 R's and there are 4 F's. The others don't repeat. So what I need to do is take all of this information. I have 8 factorial over, and then I put the repeats down here. When you solve this, you should get 840. Now, there is a formula for permutations, and it is this. And this notation might look somewhat familiar because we once had a C in a previous lesson. But now this represents permutations. And basically what this means is out of n items, R are taken at a time. So to put this in something a little more familiar, maybe we would have 5 students and 2 of them are chosen for whatever reason. Okay, that would be an example of a permutation, and this is the formula we could use. So let's say we want to find the number of permutations of the 4 letters A, B, C, and D, and 2 of them are taken at a time. And here's what I mean. So out of these 4, I'm going to pick 2 of them. So maybe I choose A first, and then maybe B, or A first and C, or A first and D. Maybe I choose B first instead, and then A, or B, C, B, D. And all I'm doing here is writing down the different possibilities. And if you look at this, I have 12 possibilities. So there are 12 permutations of these 4 letters. Well, let's look at this in a different way. This formula is n factorial over the quantity n minus r factorial. In our case, we have 4 total, and we want to choose 2 of them. So this would be 4 factorial over 4 minus 2 factorial. 4 factorial over 2 factorial is 12. Another way, a third way you could think of this is for my 4, I have 2 choices. My first choice, I have 4 letters. But then in my second choice, I only have 3 choices for that letter. And this gives me 12. So here I want to evaluate this and interpret the meaning. Okay, so evaluating it shouldn't be a problem. Let's plug it into our formula. This is 7 factorial over the quantity 7 minus 3 factorial. 7 factorial over 4 factorial. And I can write this as 7 times 6 times 5 times 4 factorial over 4 factorial. These will cancel, and I get 210. Great, but what does that mean? What this means is there are 210 ways to select 3 distinct or different items in a specific order. The order in which these are chosen matters from a group of 7 objects or items. This is a permutation. A permutation has distinct items chosen in a specific order. Here's another example. Let's say that we want to choose 2 students from a group of 4 to hold 2 positions. The first position is the presidential position. And the second position is the vice president position. So, how many choices do we have for the president? There are 4 of them. Well, once the president is chosen, then the vice president, we only have 3 choices. So 4 times 3 is 12. Try this one. A judge at a county fair must give different ribbons for first place, second place, and third place. Okay, sometimes it's helpful to draw this out. First place, second place, and third place. Well, there are 12 contestants. Of those contestants, how many of them can get first place? And there are no ties. It's all or nothing. They win or they don't. So 12 choices. Once there's a first place chosen, there are 11 choices for second place and only 10 choices for third place. If I multiply this out, I get 1,320. We also have something called combinations. Combinations are different than permutations. The reason for this is that we're still going to choose something, however, the order in which they're chosen does not matter. For example, let's say we have 15 students and we want to choose 3 of them to be on a committee. Well, there aren't any roles within the committee, and so it doesn't matter who I pick first, who I pick second, and who I pick third. They still go into this one group together. So there's no particular order. Well, when it comes to combinations, we'll see notation like this, and of course there is a formula, which is slightly different than the one for permutations, and it looks like this. So the only difference now is that we will have an r factorial. Okay, so let's look at some examples. Our first example says, how many ways can a committee of 4 people be formed from a group of 10? Well, in this case, it doesn't matter who is chosen first, second, third, or fourth. Doesn't matter. So this is a combination. So remember, our formula, n choose r, is n factorial over r factorial times the quantity n minus r factorial. So in this case, we have 10 people and we are going to choose 4 of them. So our work will look like this. And we can simplify this. And we can continue. The 6 factorials will simplify. And our final answer is 210. Let's pick it up a notch. Now let's say we want to form a committee, and this committee has to have 2 women and 2 men on it. And we are choosing from a total of 7 women and 3 men. So what we're going to do is we're going to kind of combine the things we've learned. And it's kind of like the fundamental counting principle, where we want to take the number of ways 2 women can be chosen times the number of ways 2 men can be chosen. So we'll have the number of ways 2 women from 7 women can be chosen times the number of ways 2 men can be chosen from 3 men. Now, the order in which these men and women are chosen doesn't matter. So we're going to do this piece and then this piece. So from the 7, we are going to choose 2. And from the 3 men, we are going to choose 2 of those. You do have a button in your calculator for this. This result will be 21 times 3, which is 63 ways. So there are 63 ways that this committee can be formed, given this information. All right, let's try this one. How many ways can a committee of 4 people be formed from a group of 10? But now they are going to be holding offices: president, vice president, treasurer, and parliamentarian. So now the order matters, because there are distinct offices. So if the order matters, that means we are going to be dealing with permutations. So we have 4 offices: president, vice president, treasurer, and parliamentarian. 10 choices, 9 choices, 8 choices, and 7. This is the same thing as saying, or using, this notation. And this gives a result of 5,040. This example kind of puts it together. Let's say we have 20 people who are entering a raffle. In part A, 4 people out of the 20 get $50. Don't you wish you were one of those 4? Well, in this case, it does not matter who is chosen first, second, third, or fourth. All 4 of those people get the same exact prize, so it's indistinguishable. All of the amounts are the same. If it's indistinguishable, the order doesn't matter, and so that means it's a combination. So 20 choose 4. This results in 4,845. In part B, now there are still 4 winners, but the first winner gets $50, then 25, 10, and 5. Well, these are different amounts, so they are distinguishable, and the order matters. So 20 possibilities for the $50, then 19 choices, 18, and 17. So now that is the result. I'm going to show you 2 more examples just for additional practice. Okay, so here is a lottery game, and there are 5 numbers. The numbers 1 through 39 are the possibilities. So how many different ways can we choose one out of the numbers 1 through 39? Okay, well, it does not say they have to be in a specific order. In fact, they can be in any order. So the first number chosen doesn't matter as long as you end up with the 5 numbers. So since the order doesn't matter, we'll have 39 choose 5, which results in 575,757. There is a co-ed softball team, and the coach needs to choose 4 women and 5 men from this group of people. How many ways can it be formed? Well, it doesn't matter who is chosen first and second and third and fourth and so on and so forth. It does not matter. But what does matter is the number of women and the number of men. So we're going to have 2 different combinations. 7 choose 4, because the order doesn't matter, times 10 choose 5. Again, the order doesn't matter. 32 times 252 gives us 8,820 different ways in which that coach can create his team. This concludes section 11.6.